the biogenesis and process control of m6 methylation. N6-methyladenosine is the most prevalent internal RNA modification in mice and has been found to be highly conserved and hard-coded in mammals and other eukaryotic species. The importance of m6A for gene expression, regulation, and cell-fate decisions has been well acknowledged in the past few years. However, it was until recently that the mechanisms analyzing the biogenesis and specificity of m6 modification in cells was uncovered. We reviewed up-to-date knowledge on the biogenesis of the m6 modification, including the cis-regulatory elements and trans-acting factors that determine general de novo m6A deposition and modulate cell type specific m6 patterns, and we discussed the biological significance of such regulation. The landmarks of the m6 epitranscriptome. m6 machinery from writing to interpreting. Evidence for co-transcriptional m6 deposition. Histone modification guide m6A deposition in CDS and 3' UTRs. H3K36 M3 m6A crosstalk in mouse and embryonic stem cell pluripotency. Transcription factors modulate cell context-specific m6 methylation. Concluding remarks and future perspectives. Inspired by the discovery of histone and DNA demethylases, methylation was shown to be reversible as early as 2008, when FTO was reported to be the demethylase of M3U. M6A was later found to be the dominant substrate of FTO in the nucleus that undergoes reversible regulation in cellular. The biological significance of RNA modification, especially of m6A, has been well acknowledged in various physiological and pathological processes. However, how they know m6A RNA methylation is precisely deposited was not known until very recently, when accumulating evidence suggested that histone and transcription factor signatures on chromatin together shaped the m6A epitranscriptome. Generally, m6A deposition on most m6A containing transcripts occurs in a sequence and H3K36 ME3 marked dependent manner, which maintains the conservation and CDS 3' UTR erasement feature of m6A. During splices processes, transcription factors through different action on m6-MTC, but at erasement or exclusion of m6A on specific transcripts that are necessary to execute specific biological function. Together, this distinct mechanism enables the inheritance and plasticity of m6A methylation. Compared with the well-studied DNA cytosine methylation, m6A methylation has its unique characteristics. The no DNA methylation and maintenance are achieved by different DNA methyltransferases. DNMT3A/B and DNMT1, respectively. DNMT3A/B generates new methylation site to fulfill the requirement of dynamic regulation, whereas DNMT1 faithfully copies the methylation patterns from the mother strand during DNA replication. Unlike DNMT3A/B and DNMT1, which can catalyze DNA methylation alone but function in different processes, metal-3 and metal-14 must work together to catalyze m6A methylation and may exhibit a new function other than as methyltransferases. For example, metal-3 alone could function as an m6A reader to promote translation by recruiting EIF3 to the translation initiation machinery, allowing more complex and flexible regulation of gene regulation. In addition to the 5MC modification, a modified nucleotide more similar to m6A has been reported in DNA. N6-methyl-2-deoxyadenosine, which is catalyzed by a different methyltransferase, N6-AMT1. It will be interesting to investigate how metal-3, metal-14, and N6-AMT1 could specifically deposit a methyl group on adenosines in RNA and DNA respectively. Collectively, crosstalk between heteron H3K36 and IM6 methylation uncovered a new layer of gene expression regulation, adding M6 methylation to the complex epigenetic regulation network. By carefully studying the relationship between m6A RNA modification and other epigenetic modifications, future crosstalk is expected to be uncovered in the near future, enabling comprehensive understanding of the entire epigenetic regulation network in various essential biological processes as well as in pathogenesis.